It's the exact same as yesterday. It's really close. Let me just rewind a little bit. You remember when we did vertical translations? Positive was up and negative was down. Easy. Life was good. But then when we did horizontal, positive went left and negative went right. It did the opposite of what you're going to think it was going to do. I'll just mention that as we go through this. We'll go through the whole investigation as if we don't see that coming. But
Sorry, thank you.
I just mentioned that might be something that comes up today again too. So anyways, if f of x equals x squared, complete the following tables. Instead of using root x, I decided to use x squared today as my test function. So squaring all these numbers. Hopefully this is old news by now. 9, 4, 1, 0, 1, 4, 9. Yeah? To build a table of values for y equals x squared. We don't need any special x values. Not like root x where we got to watch out for things. F at 2x. Careful now. This says wherever you see x, write 2x. Only the x gets multiplied by 2. So this is the function 2x squared. What does that do to the whole thing? And you may have a theory. You may have a theory. Well, let's check it out. 2 times negative 3, then square it. 2 times negative 3 is negative 6. Squared is 36. Maybe you need extra steps. Maybe you're going to jam it in your calculator. I'm trying to stay young and do them in my head. I don't know if it's working or not. Next one. 2 times negative 2, all squared. 2 times negative 2 is negative 4. Squared is 16. Uh, 2 times negative 1. 2 times negative 1, all squared. 2 times negative 1 is negative 2. Squared is 4. I'm really unhappy with how neat that came out, my 16, so I'm just going to fix that up. So I'm not changing it. I'm just writing it neater. All right. I keep going. 2 times 0 squared? Okay. Well, I don't know. Maybe I don't need all that writing for that one. I wrote it anyways. 2 times 1, and then square it afterwards. See, I'm phrasing that differently now to try to help you understand what's happening. The multiplying by 2 is before the squaring. That's important. Now, 2 times 2, which is 4 squared. I'm up to 16. And 2 times 3 squared, which is 6. I get 36 again. Again, my 16s are terrible today. Let me fix. Equals 16 equals 36. Let's not go any farther. Actually, what I am going to do is fix this so my colors match up. I'm not changing anything here. I'm just changing this all to orange so my colors, you can see the difference between the colors here. Actually, let's make a prediction before we, let's not look at the table of values. Let's make a prediction here. Multiplying by 2, what would your intuition say is going to happen to this thing? Divide by 2, and you're a step ahead of us. Why do you think it's divide by 2? Okay, so let me just take the other side and then just get a little more explanation from him. That says multiply by 2. Wouldn't that be multiplying things by 2? You're saying it's dividing things by 2. Like it literally says multiply by 2 there. So why are you suspecting that it's going to be divided by 2? Oh, he's looking at this one. He's looking at this one. Okay, I'm back to this one. What would your intuition say? What's your brain going to tell you is going to happen here if I'm going to be multiplying x values by 2? It's going to double things. It's going to stretch them out. That's what your intuition says, is that this would stretch. Okay? Let's graph them both and see what happens. First one. You've got a graph paper right underneath, right? You don't have to switch pages like I did. First one, regular y equals x squared function. 0, 1, 1, 2, 4, 3, 9. You'll notice I'm not looking at my table of values. I'm so good at x squared, I don't need my table of values anymore to do that. Should you use it? Well, I don't know. It depends on the question. It depends on what you're doing. Maybe you do want the table of values. I'm not putting down the table of values. I'm just noting that there are some functions that you can get good at where you don't need Now, no cheating here. I'm going to do what it said. It said, okay, in blue now. I've got the colors matched up. I missed that the first time. First point, -3, 36. Off the page. Now, is that helpful? Well, yes, sort of. I sort of know where that next point's going to be. So when I draw this thing off, that'll be helpful. But the first one I can do on my graph is -2, 16. -2, 16. -2, 16. I was put in the wrong spot there. Would have messed up everything. Oh, goodness gracious. What was the next point? -1, 4. 0, 0. 1, 4. And 2, 16 is the last one that fits on my page. Now, you say the 336 isn't helpful, but it sort of is helpful. It tells me that I just go right off the page now. That is some information, but you'd be right in saying it doesn't help me draw my graph. It just makes me feel confident that that's what's happening. Our intuition told us this would stretch the x, but that is not what happened. What happened to the blue graph? It compressed. Okay, so that goes against our tuition. But how does it fit in with what we've already seen this chapter, though? If we think back and put the whole chapter in context, what happened before? Let's see. When it was outside, our intuition worked. Yeah, let's just go back here and just put a little thought bubble up here in purple. If I went y equals x squared plus 2, that was up 2. That, our intuition was correct. Vertical, the intuition works. Horizontal, though, when we did horizontal, when we did x plus 2 there, x plus 2 went left against intuition. I'll put a little sad face there going, that didn't work right. The horizontal didn't do what we expected it to do. So could we have predicted that it was going to happen here again? No, I don't know. Maybe not. But we shouldn't be all that surprised that the horizontal does the opposite of what we thought it was going to do. This multiply by 2 compresses it by factor 2. Anyone ready to make a prediction on this one? What's going to happen here when I do a half in there? It's going to stretch. Yeah? So that's the big deal. That's part of this juggling act we're doing this chapter is going, oh, the horizontal ones always do the opposite of what intuition would tell us. So if I was going to write this function, I'm going to do in red. You don't have to do it in red. Maybe you're doing light and dark. I would go half x before squaring. I call it inside the function, but I'm getting better at phrasing it as I go along for students to say before the squaring. That's what inside means, before squaring. Yesterday, the multipliers were always out front after the squaring. That was vertical. Okay, half, oh, can I do these in my head? I don't know. I'll try. You don't have to. You can put it in a calculator. So this would be half of -3, then square it, which would be -3/2 squared, which is 9/4, which is 2.25. Do I have to show all that work, Mr. Todd? Well, I don't know, but that's just all that's going on there. I just need the value, really.
Oh, I have a question.
Yeah, tell me your question.
Is it just like divided and then there's like multiplication by like 4? For these examples, like with 2x and then half. It's like they're both like, it's like 9 times 4 is 36, and then 9 divided by 4 is 2.25.
I'm not sure what you mean.
Because it's like the y is getting like multiplied by 4, but then it's getting like divided by 4. Because it's like,
Oh, yeah. Yeah, but you're seeing something I won't quite cover today. But no, that's not true. In a second, ask your question again, and I'm going to do something that I'll do it right at the end, okay? After I finish, somewhere along the way, ask me again, and I'll do a little something here that might blow some people's minds. That works on parabolas only. You're seeing something that works on parabolas only. There's something weird about parabolas. And it doesn't usually happen. But I'll get back to it. I think I know what you're asking. I'll get to it in just a second. Let's see. Half of negative 1 squared would be negative a half squared, which is 1/4. 0.25, I guess, if I'm going to try and graph it. Maybe you need the 0.25. Is everyone okay if I just write 0 there? Half of 0, 0 squared, 0. You know, that's not going to do anything. And then half of 1 squared is half squared, which is 1/4, which is 0.25. All this stuff is true, but maybe you want the 0.25. Maybe decimals are what you want here if you're going to go graph it and put it on the page. This one's better. Half of 2 squared is 1 squared, which is 1. And half of 3 squared is 3 halves squared, which is, again, the 9/4, which is 2.25. What's our prediction? What's going to happen here? Half makes us think stretch. Counterintuitively, because it was horizontal. So you got to remember that in this chapter. The horizontal ones do a counterintuitive thing. We got a flavor in our little dance thing of why that is. The function's looking right, so it moves left. It's doubling the x before it's squaring, so it's looking outwards, and that makes it go inwards. Is that a good explanation? For grade 11, it's about the best we can do, I think. Yeah? It takes a little while for it all to be clear why this is happening. I'm going to go back and forth. So if you haven't got these, I'm just going to go back and forth and use the points. Negative 3, 2.25. Negative 2, 1. Negative 1, 0.25. And 0, 0. And the other ones are symmetrical, so I don't need to look back for those. But you can check on your graph that you get the same ones. Is it good enough? Are you going to want some more x values here? This is what I was trying to allude to the other day is negative 3 to 3 might not be all the x values you want. But they should be enough to make you go, oh, I know what x values I need. Awfully tempting now to extend this table of values and add some x values here. I like negative 4 and positive 4. I like negative 6 and positive 6. I didn't see right through this. Why did I skip? Why 4s and 6s?
because you get half out of it.
Yeah, those will be nice numbers, won't they? Because then I'm not getting the 0.5s in there. And maybe now that I've seen this, if I was to rebuild this table of values, maybe I just would have used even numbers. Maybe. The decimals are fine. There's nothing wrong with them. It's just they're not as convenient. So if I do half of negative 4, squared, I get 4. Half of 4 is 2, squared is 4. Half of negative 6 is negative 3, squared is 9. And half of 9. So I get negative 4, 4, and 4, 4. Is that going to help here to see the picture? Negative 4, 4, 4, 4, yeah. And what was the last one I got? Negative 6 and 9. I don't want you to think I did any magic there, because I really didn't. I just kept the table of values going. If you understood the table of values that I had, I just went a little farther with it. 6, 9. Did we get what we expected? No. Did we get what we unexpected? No, I'm not saying that right. Are we surprised but not that surprised? that this did the opposite. That actually sort of fits in the puzzle we're building. That horizontal would do the opposite. But back to the table of values if you need that. Do you need the table of values? Do you need the table of values? You good? How are the graph of f at 2x related to graph of f at x? When I multiplied by 2 in there, and I went from orange to blue, and I'll answer that in blue here to match up, what actually happened here? Maybe using the fancy words from yesterday. From orange to blue, a horizontal compression factor. Now, if you wrote 2 here, I'd be like, yeah, you said compression, so I guess I'll give it to you by using 2, but it wasn't really a compression by factor 2. What happened to the x values? 2 became 1. 4 became 2. It was actually a compression factor 1/2. I've actually flipped the factor that was there. 2 over 1 becomes 1 over 2. That's how we reverse it. How is the graph of f of 1 over x related to f of x? This one was a horizontal stretch by factor. Okay, big help coming here. Big help coming with these questions in red. Here's some help. By factor 2 over 1. Do you need the 1 there? No, that's just me trying to help with what's happened there. The roles of the numerator and denominator have reversed in the horizontal, so this 1/2 factor that was there becomes a stretch by 2 over 1. Yes, that's 2. I totally get it's 2. But if the homework question is 2/3, I want you to know that it's flipped. That's why I wrote 2 over 1 there. So we have a pretty simple procedure here that matches up with yesterday, only it's just the opposite, that's all. To sketch the graph of f at 2x, we can multiply the x values of f at x by 1/2, which is the same as dividing the x values by 2. This note should be beside you as you're doing your homework. You know, as you're going through, what do I do here? How do I handle this? Really good guide here today. It's a good walking you through the steps type thing. And then to sketch the graph of y equals f at 1/2 x, we can multiply the x values by 2. But do this in your notes to help yourself on tougher questions. Change that 2 to 2 over 1. It doesn't really change what you're doing, but it tells you what's happening. 1 over 2 became 2 over 1. That's what's really happening is you're flipping that stretch factor. Okay, so one of the first things somebody said, is this the same as yesterday? Almost. It's horizontal instead of vertical, but everything's flipped in the sense that if it was going to be, if it looks like stretch, it's actually compressed. If it looks like compressed, it's actually going to be stretch, which is weird. And that is weird all the way through math on that. Do you have questions there? Can't tell. Dion's thinking. He's asking a question. What's happening?
So like, if we were to do this on a test or something, would we just be able to draw the normal one and then do all that?
Dion's graphical. He says, just graph it and then just double the x values or double the y values or half them or whatever. And that's graphical people will. That's how they'll do it. And I love that. Yeah. But I'm going to also show a table of values method as well. Some people don't like the graphs, working on the graphs as much, or the visualness of it confuses them as they're trying to do math. So I'll show a table of values method as well. So I'll give you 2 different options on how to actually manage this. Okay? Questions there? Extension. What if it was a 3? If you want to do y equals 3x, we can multiply the x values by 1 over 3, which is the same as dividing the x values by 3. And if we want to do y equals 1/3 x, we can multiply the x values by 3. But what am I going to do to this 3 to try to help you? 3 over 1. Really what's happened is that stretch factor has been flipped. See, this was 3, and it became flipped 1 over 3. This one was 1 over 3, flipped 3. That will solve a lot of your problems. If you just go, oh, we flipped the one, the horizontal one. The vertical one we keep the same, but the horizontal one we flip. That sort of matches up with before, right? Vertical, we keep it as 2 when we're going up or down. Horizontal, we do the opposite. We don't do 2, we do left. We do -2. Yeah? Okay. So it does kind of all match up, except for the fact that horizontal does the opposite of what we think it should do. Yeah? More time there on slide 3 of 5. Whoa. We could be done early. Wouldn't that be nice for once? Yeah? More time? In general, though, so I did 2s, I did 3s. It's true for all values of b inside there. If b is bigger than 1, it's a compression by 1 over b. If b is between 0 and 1, it's horizontally stretched by a factor of b. No, 1 over b. Yes, sorry, 1 over b. That was right. Sorry, I thought they were saying something different there. 1 over b. And all this is saying here, don't let this 1 over b confuse you. All we're saying here is flip. Both those are saying flip that thing. Dion. That's tomorrow's lesson. Tomorrow is combining all these. And I think I touched it a little bit in this chart here. Just a little bit of, ooh, what if I've got 2 going at once? Let's go back to Kyle's question. In some situations, depending on how symmetric the graph is, y equals x squared is very symmetric. Look, if I just did this algebraically, 2x could be written as 4x squared, which means a horizontal compression gives the same graph as a vertical stretch. Let's look at our graph here. This blue one that was horizontally stretched or compressed by factor 2, I could have done it as a vertical stretch factor 4. Not all functions will do that. Parabolas do because they're very symmetrical. Even functions do this. So don't get addicted to that. But in the case of y equals x squared, it could have been either way. OK, 2 examples just like yesterday. The first one I'm doing just like Dion suggested. Exactly like Dion suggested. Right off the graph. I'm not going to go to table of values. This one I'm going to do both ways. So you have 2 weapons available. I could do it off the graph, or I can do it off a table of values. The first thing to do, always, put one of these little dots and go, OK, what transformation are we talking about? If it's f at 2x, what do I have to do? Multiplying by 2 inside. Is it vertical or is it horizontal? Horizontal. It's horizontal. Not because today's lesson is horizontal, but because it was inside. The inside ones are the horizontal ones. And it's multiplied by 2. Intuition says multiply by 2 means stretch, but because it's inside, this is a horizontal compression by factor 1 over 2. Flip that thing. And then I'll put a little extra in there. Could I just divide by 2? And the answer is yes. So you can do whatever you want. You can multiply by half or divide by 2. So I go to each of these x values and just divide them by 2. This is what Dion was, he was sort of motioning in the air. He's sort of going like this. Can I just take the x and just compress them? Yes. -4, -2 becomes -2, -2. -1 becomes half of what it was. 0 stays right where it is. 3 becomes 1.5. 5 becomes 2.5. 7 becomes 3.5. Ooh, I feel like I made a mistake. Let me just check. 2.5, 3.5, Yeah, and when I draw, and you might not be able to see it. You might be looking and go, I don't really understand what's happening. I've done what you said, but when you connect up the lines, hopefully you can see what's happened here. It's the same function, essentially. It's just been compressed. It's been squeezed together. It's like somebody grabbed either end and squeezed it all together. It's got the same two triangular bumps there, but the triangles are less wide. It's got the same little push-off thing on the side here, but it's all been compressed. Now, on the way to work today, I was listening to Cupid. Have you heard this song?
I thought you were listening to Drake.
No. No, I don't hate myself. But have you heard the songs that are like the sped up version? Like when they have a song and then they have the sped up version of it. And the people who are singing sort of sound a little chipmunky, a little bit high pitched there. This is what's going on. We've horizontally compressed everything, and now everything sounds shorter wavelength, and then they sound like they're a higher frequency. That's all that's happened there is they've compressed it. They've horizontally compressed the whole song. Okay, this one, 2 ways. I don't know, don't prejudge. Everybody's different. Some people like to use a table of values to do the compressions and stretches. Some people like to do it right off the graph. So check it out. Here's what I'm going to do. I'm first going to build a table of values for the base function. There's only 4 you have to choose from in 11U so far. But in this chapter, there's only 4. Which one's this? Is it obvious? It's got a root in it. Yeah? Where's the sweater? It's got the, she's got a root sweater. Root x. And you go, okay, I see there's a 1/3 there. I will deal with that. But for now, I'm just going to do y equals root x and build my table of values. Hopefully, you're getting to the point where it's like, you know what values to put in for y equals root x. You don't put in -3, -2, -1. That's not going to help things at all. And you go 0, 1, 2, 4, 9. Do I have enough room for 16 here? Yes, I do. 16. And then I just square root them all. I get 0, 1, 2, 3, and 4. Okay? Now stay with me. I'm doing this both at the same time. Graph people then will go, okay, I have the base graph. And they'll go over there and they'll go 0, 1, 4, 2, 9, 3, 16, 4. And graph people enjoy this, actually. They like this procedure of putting the graph on there first. And going, okay, now that I have my graph, I can do my transformations. What is the transformation? There's only one here today. A 1/3 inside. First of all, is it horizontal or is it vertical? Horizontal because it's inside. Second of all, my intuition tells me 1/3 would compress this thing, would make it smaller, but that's not what happens. This thing is, and I'm going to put it right up here, what I'm after is a horizontal stretch factor 3. Get ready. I'm going to do it both at the same time. So you can do the graph or you can do it on the table of values. Table of values people will be like, oh, horizontal stretch factor 3. I go right here. I go horizontal stretch times 3. And I just take all those x values and multiply them by 3. That's all. 0, 3, 12, 27, 48. Table values people are very happy at that point. You just graph, see, I gotta cover that up. They graph 0, 0, 3, 1, 12, 2, 27, 3, 48, 4. Done. They like that. Table values does all the work for you. Graph people are like, wait a minute, I don't need this stupid table of values. I'm multiplying x values by 3. So I take this 0, 0, it stays there. This one has x value 1. So I multiply it to x value 3. This one has x value 4. I multiply it to x value 12. You know, you can feel the stretching going on as you're doing it. It really is quite a visual thing. And then 9 becomes 27, which seems like not good information, but it actually is. It tells you, whoosh, right off the page there, Mr. Todd, both methods are fine. Which one do you think is better, Mr. Todd? Table of values will probably get you more right answers quicker. Graph will help you understand what's actually happening. Table of values can seem magical sometimes if you're just plugging numbers in. So I don't say one's better than the other. They each have their advantages. What questions do you have? When there gets to be more than one transformation, the table of values stays this difficult. The graph takes a little bit of work if there's more than one transformation going on. But that's tomorrow's lesson. We don't have to quite panic about that just yet. I thought it was 5 slides, but this says 6. Did I keep saying it was 5, or was I say 6? Do you need more time here? Yeah? What day of the week is this? Wednesday? When did I say the quiz was? Monday. Okay, because the quiz covers everything up to the end of tomorrow.
So this is the regular one?
Yeah?
Yeah, you multiply the x values by 3. So right now, this x value is 1.
Yeah, and then you multiply by 3.
So that point would be where 3 is.
Yeah.
Then where's this x value is 4, you multiply that by 3, you just get 12.
Oh, that's what happened.
And then this x value is 9, you multiply it by 3, the next point would be 27.
All over it, buddy. All over it.
I just wrote it wrong in the graph.
Okay, good stuff. More time? Are we good? Good? Okay, there, quiz hint. The quiz has got a chart like this on it. You know, you have to walk through it. I don't like how big it is, so I'm going to vertically and horizontally stretch it. Incidentally, whoever programmed this computer to do that, when I'm pulling on that like that, they're doing the exact math we're doing here. They're taking this picture and multiplying the x's by 2, the y's by 2. Look, the first one's been done for you. Y equals square root of 4x. If the base function's root x, it's a horizontal compression factor 1 over 4. Flipped. Second one's been done for you. If it's a 1/5 in there, flip that over to 5 over 1. You don't have to write the over 1, but it might help you to think these through, to think of it as 5 over 1 when you first write it down. So, y equals 1/4 x squared. What's the base function? Y equals x squared. Identifying the base function shouldn't be too bad in this chapter. There's only 4 to choose from. Squared, square root, regular x, or 1 over x. That's all you got to worry about there. So what's the transformation? There's only one here.
It's a horizontal stretch by a factor of 4.
Horizontal stretch factor 4. I need to tell you that if we get this nailed down now, why we're taking so much time on this here is because in advanced functions, every chapter, not every chapter, pretty much every chapter has a section on transformations. We learn a new function, and we say, okay, let's do transformations on it. And you'll be bored as heck if you get it now, because you'll be like, oh yeah, transformations, I got this. Corresponding base function, y equals x, and I've got to horizontally stretch it by factor 3. Technically, I should write that then. But what? 3x is the same as 3x. To which you go, is it, what's that? Oh, right, 1/3. Horizontal stretch factor 3 should be but that's scary. You're like, what? That doesn't look any different than a vertical. How am I supposed to know if it's horizontal or vertical? Well, maybe we need a little help from Desmos to understand how easy and hard lines are at the same time. Y equals x. Yes? Y equals 1/3 x. Let's just zoom in here and see what's happened. Is the blue line, stay with me here, because it's a trick question. Is the blue line a vertical compression factor 1/3, or is it a horizontal stretch factor 3? Which way works? The answer is both. Lines are weird. You could be thought of either way. They're too simple for this procedure. There's nothing crazy about them, so they're like, yeah, whatever you want, it's fine. It's the same either way. This can be thought of as a horizontal stretch factor 3, or it can be thought of as a horizontal compression factor, horizontal stretch factor 3, or it can be thought of as a vertical compression, and it's the same difference either way. You get the same thing. So don't let lines mess you up. They're too easy for this procedure. They maybe shouldn't even be in this chapter. They were supposed to be in grade 9 because they're simpler than all this. Yeah? All right, 1 over 5x. What's the base function? Squared? Square root? X? It's got to be 1 over x, yeah. The x has been multiplied by 5. Therefore, this is a horizontal compression factor 1/5. And I'll put a star beside that one because if that one bothers you, I get it. That is a very weird one. But what you have to look at is the x got multiplied by 5. And if the x got multiplied by 5, it's a compression. Horizontal compression factor 1/2. Vertical translation up 4. Here we go. This is where this lesson starts to be tomorrow's lesson. How about two things at once? If it's a horizontal compression factor 1/2, it's got to go inside the squared. But it's not a 1/2, it's 2. But what about up 4? What does up 4 do to all this? Outside plus 4. See, that's the juggling part where you start to go, okay, I got 2 of these going at once. Usually the up and down people find to be the easiest transformation to do. 3 more to go. 3 square root, okay. I don't have any wisdom here. If you see square root, it's the square root function. But here we go, 2 transformations. Let's do yesterday's first. The 3 out front is the vertical one. Vertical ones are easy. Vertical stretch factor 3. If you did the homework last night, you're like, most of it was pretty straightforward. There's a couple of tricky questions like 8 and 10. I think things got a little crazy for a minute, but vertical stretch factor 3. What about the 1/4?
That turns to a 4.
Right. Horizontal stretch factor 4. How did you get 4, Kyle?
It's inside the thing and it's 1 over 4. So
Right, so 1 over 4
we flip it.
becomes 4 over 1, which is 4. Oh, 3 transformations at once.
Oh, I got this one.
You going for it? All right, Kyle, tell me the whole thing. Y equals,
So it would be y equals 2.
hold on, 2 going outside the function because that's a vertical stretch. Yeah, good.
Bracket
Yeah,
3. like 3 bracket x bracket, then another bracket.
Not wrong to put the bracket in there,
Okay,
but
then
unnecessary. Squared?
2. Yeah. And then minus 5
Minus 5.
because that's outside, so it's just.
Yeah,
Is that right? Is that bang on?
bang on. Bang on.
I kind of got confused though with like, cause like when it says like vertical stretch of 2, it's like, cause in my mind like I'm flipping the horizontal, so then I think, oh, I'm gonna put like.
Flip the horizontal, leave the vertical the same. Yeah, and it's the same with translations. Switch the inside one, but don't switch the outside one. Okay, you could write f at x here, but that messes people up. When they write something like this, all they mean is you don't really know what the function is.
Oh.
So it's an unknown function. It's not wrong to write f at x. You're just saying, I don't know whether it's x or x squared or root x, 1 over x, doesn't matter. All I want to know is what transformations do you see. So how many is there?
4.
Harry says 4.
There's 4.
1, 2, 3, 4.
There's a negative.
You look at them and decide which one. Let's try and do them in the opposite order of difficulty. After all this time, what's the easiest one to see?
Vertical translation is not gonna.
I think he's right. Vertical translation,
-1.
op 7. I think that's the easiest one to look at and see what it is. What's the next easiest one?
Vertical reflection.
I 100% agree. Vertical reflection in the x-axis. Next easiest one, Kyle.
Horizontal compression by a factor 3 over 2.
I disagree with him. I don't think that's the easiest one.
That's the harder one,
But
he's right.
he's nailed it. He's nailed it.
But the vertical one.
Horizontal.
Oh,
Ooh.
this one.
Horizontal blank. I'll let you think about that for a second. Horizontal something, factor 3 over 2. If it's factor 3 over 2, is it a stretch or a compression? I forget what you said.
Oh, it'd be a stretch.
It's actually a stretch. Because it's bigger than 1, right? If you're multiplying by something bigger than 1, you're going to get bigger.
1
And the one he skipped over,
The easy one.
which we think is the easy one, vertical, it's factor 2/3, so it's a compression. Are you getting a flavor for why the juggling is going to be difficult? Pulling these things apart can be a little bit tricky. And we do a whole lesson on it tomorrow. How are we going to pull these things apart? But I gave you a taste of it here today.
Wait, why isn't it y equals x though?
What we're saying is some function is going on here. Maybe the function is root x. Maybe it's 1 over x. Maybe it's x squared. Maybe it's sine x. Maybe it's cosine x. I don't know. So in a question like this, they're saying, don't worry about what the function is. Just tell me about the transformations you see.